Okay, today we're just going to piggyback on what we learned yesterday on continuity and one kind of new concept. It's going to be called a removable discontinuity. Okay? For the most part, if we're doing this by hand, it's going to happen when something is reduced out of it. So the only one that had a removable discontinuity from yesterday's work was number 6. So let me take a close look at number 6 to introduce this. Okay, so if we were to take a look at this graph, I have it thrown in here in my y equals right now, my graphing calculator. We see an obvious asymptote and a point of discontinuity at x equals 2. And when we factored it, we could see that that was visible. But what about 5? That's not quite as visible. Let's kind of zoom in a little bit more. So if I trace closer to an x value 5, I'm getting there, and try to zoom in on this area, zoom to enter. Still, it's not noticeable. It's supposed to be an open circle. Okay, you may remember learning that in Algebra 2. If something factors out of a rational function like this, it's supposed to be an open circle at that spot and undefined. Okay, it's even giving me a value of 0.333. It should be undefined because we just went over that here, that it is supposed to be discontinuous. Okay, so if you can kind of remove it algebraically, then they call it a removable discontinuity. Okay, the other one's not. It wasn't removable, the x minus 2. Okay, if it's a piecewise graph, basically anytime we have an open circle here at this spot and it still has a limit, we'll also call that removable. That can be a little confusing. We'll get there in a moment. But for now, if we're looking at an algebra problem and they ask you which ones are removable, here we'd say x equals 5. It's still discontinuous at both spots. Like I said, it's an open circle at that spot. But which one's removable, we'd have to say the removable one is at x equals 5. That's all. Okay? So it might not have one. For example, number 1 is a quadratic function. You could throw it in your graphing calculator to verify. This one's going to be a little bit tougher to use your prior knowledge. You want to throw that in your graphing calculator and check. Does it look continuous or not? It is. So find the x values at which f is not continuous. This is continuous for all x. So continuous for, you could say all x, or maybe you want to say negative infinity to positive infinity. That will be the answer sometimes for some of these problems. There is no which of the discontinuities are removable. I didn't state any discontinuities, so we don't really have an answer to that part. Okay. Let me jump to one that does have a removable discontinuity. Let's go to 4. Up top, we can take out a GCF of 2. On the bottom, we have difference of 2 squares. So right now, when we get it in factored form, we should see some obvious numbers that create 0 on the bottom. And so we know if we punch that in our graphing calculator, we could see asymptotes of that spot. But actually, since one of them is removable, we'll have this situation again where it's going to be a hole. So we won't see them both. So that's why it's important to do it by hand, because a graph sometimes you can't see it. You'd have no idea that this x equals 5 was a discontinuous spot. All right, so we can see how this cancels out. So we know it's discontinuous at x equals negative 3 and positive 3. The removable discontinuity, I'll abbreviate a little bit here so I have some room. Removable discontinuity is x equals, take a look, which one did we cross out? Negative 3 plus the 3 is 0, right? So negative 3 is the removable one. Okay, and if I were to throw that in the calculator to confirm, I'd see an asymptote at x equals 3, and then I wouldn't see much of anything at negative 3 because it's going to be a hole at that spot. Okay, so that's how we answer this scenario. So you kind of just move forward, just like yesterday's lesson, to get your points of discontinuity, and then which ones are removable. Okay. All right, let's you pause and try. Let's try number 9. And then maybe we'll take a look at a piecewise graph to finish. All right, feedback on 9. The bottom, we're looking at factors of 8 times c. So factors of 6, they add up to 7. So it's 6 and 1. Split that middle term, factor out the GCF factor by grouping to get this factor. Okay, so that factors to this. So I replaced it here. Okay, and then these are the removable. So it looks like there's 2 x values that give us 0, right? I said x plus 3 equal to 0, solve it. We get negative 3. Take 2x plus 1, set it equal to 0, solve it. We get negative 1/2. But that is the removal of discontinuity, which you wouldn't be able to see that on the graph. Okay, so basically the limit does exist. If we have a hole, a scenario like that where they are connecting or converging on the same number, it's another way to tell that it's removable. Okay, so a removable discontinuity at x equals negative 1/2. Maybe I should show you that graph too here in just a second. Okay, so let me let you guys write this down. So in summary, and I'll show you this with number 4, and we'll talk about it in the piecewise here to wrap it up. It is removable if basically the factor is reduced, right? The 0 that's associated with that factor is reduced. I wanted to summarize it. I don't want to get too detailed, but the 0 from where that one was associated with, if that was reduced, then we call that removable. That one's the easy one to see. Okay, the other scenario is if the limit still exists, because this would be maybe you're looking at a graph where you're not sure if it was factorable, but the limit does exist even if the function is undefined for that a value. So you might be wondering, when would that happen? Well, 12 is actually a scenario where it might happen. I'll walk you through 10 and then kind of give you a heads up on maybe 12, because f of a is not, remember these piecewise graphs, we look at the borderline for the possible points of discontinuity. And x at 0, there's no line underneath here. It doesn't look like it's defined as 0. So both of them have kind of open circles. But if they meet, the open circles meet like your last quiz, and the limit does exist, we'd call it removable. Okay? All right, but let's go ahead and just go back through how we do 10. Sorry about the crazy looking bracket. I'm not sure what happened on the font. This is nothing new. It's just a normal bracket for the piecewise graph, okay? All right, so remember you kind of have 3 options for doing these piecewise graphs and figuring out if it's continuous or not, or graphing them. We can graph them by hand. We can use the graphing calculator to help us. We can create a table on our own. But if we're just doing a limit for this, I'd use the table. But let's look at them all in the graphing calculator. Sorry to be stumbling here, but I think I have them all set up and ready to go. I've got lots of functions in here. By the way, if you didn't know you could do this, you could punch in multiple functions and just hit enter on your equal sign and get rid of the one you don't want and the ones you want. So I've got 1/2 x plus 1. Up here at the beginning, so I'll turn that back on. I got the condition set, and then I've got 3 minus x on here. And so now I'm going to graph that. So here's the graph. There's 1/2 x plus 1, and the other one looks like there's a little gap here. It looks like the limit is not going to exist, so it's going to be discontinuous, right? I could zoom in on that area if I'm not sure. I want to take a closer look. Let's go over here, zoom to enter. We can also look at the table here in a moment to see. So it looks like it is discontinuous at x equals 2. We just confirmed it with the graph, right? Because the limit does not exist. Okay, if I go to my table setup and take a look at that a value of 2 and keep these small increments, we could also confirm this way. Okay, these y values, as it's closer to 2 from the left, are going towards 2. And then from the right, this is getting closer to 1, not the same value. Okay, So now we're ready to answer that. Find the x values at which f is not continuous. This is discontinuous at x equals 2. It was not removable. The only way this would be removable for a piecewise graph is if these connected with an open circle like this, or a closed circle, I guess. Now it would be continuous then if it was closed circle, so that would make sense. So let me just create this scenario and let's just say it had this, they did connect at an open circle. It is discontinuous, but if that happens and the limit does exist, then we say it's removable, okay? But it didn't happen. It might happen for 11 or 12. Now, let's let you see if you can figure that out. Okay, your assignment is just to finish the rest of this page, 1 through 12, and then I'll give you feedback on that tomorrow.